Hello everyone, I am Lizelle Pilapil. We are the group 1 and we are going to tackle about the solution of ordinary differential equations, the initial value problems. Okay, when we say the initial value problem is a differential equation with where is an open set of together with a point in the domain of called the initial condition. So a solution to an initial value problem is a function that is a solution to the differential equation and satisfies. So the further discussion together with the examples will be discussed by my group members.
So now we're going to talk about the Euler's explicit method. Explicit methods calculate the state of the system at the later time from the state of the system at the current time without the need to solve the algebraic equations. For the forward method, which is from this point on forwards, Euler's method will be known as forward. We begin by choosing a step size. The size determines the accuracy of the approximate solution as well as the number of computations. So we have here a example where we are going to solve it using Euler's explicit method. So we have here its equation and its condition. So we're going to calculate y1 and y2 when x is 1 using the Euler's explicit method. With its considered step size, which is equals to 1, and where y1 when x is 0 is equals to 2, and y2 when x is 0 is equals to 1. So we're going to calculate y1 when x is 1. So we have here y1 when x is 1 is equals to y1 of 0 plus f when x is 0, xi is 0, which is the value we know, and yi when x is 0, 1 is 2. So we have here an equation amount times the step size, which is 1. So y1 when x is 0 is equals to 2. We have here in its condition y1 when x is 0 is equals to 2 plus x, which is equals to 0 times y1, which is 2, minus the 3 times y2, which is 1, times the step size. We have here in this condition. And then we will get y1 when x is 1. So we have here the answer of -1. So in getting the y2, the same idea goes with y1. So we have here y2 when x is 1 is equals to y2 of 0 plus f, where x is 0 is equals to y1 when x is 0, and y2, which is 1, times the step size of which is the value of 1. So y2 when x is 0 is equals to 1. Let's see we can see in its condition where y2 when x is 0 is equals to 1. Plus 3 times y1, which is 2 minus x squared, which is the value of x is 0. So we have here x 0 squared times y2, which is 1, times its step size 1. So we have 1 plus 6 minus 0 times 1. So we have 1 plus 6. So y2 when x is 1 is equals to 7. So that would be all in this problem. Using the Euler's explicit method. So we have here its equation and its condition. So we're going to calculate y1 and y2 when x is 1 using the Euler's explicit method with its considered step size, which is equals to 1, and where y1 when x is 0 is equals to 2, and y2 when x is 0 is equals to 1. So we are going to calculate y1 when x is 1. So we have here y1 when x is 1 is equals to y1 of 0 plus f of when x is 0 xi is 0, which is the value we know, and yi when x is 0, y is 2. So we have here the equation above times the step size, which is 1. So y1 when x is 0 is equals to 2. We have here in its condition, whereas y1 when x is 0 is equals to 2 plus x, which is equals to 0, times y1, which is 2, minus 3 times y2, which is 1, times the step size. We have here in this condition above. And then we will get y1 when y and when x is 1. So we have here the answer of negative 1. So in getting the y2, the same idea goes with y1. So we have here y2 when x is 1 is equals to y2 of 0 plus f, where x is 0, the same goes with the y1, x is 0, and y2, which is 1, times the step size, which is the value of 1. So y2 when x is 0 is equals to what? Let's see in it, we can see it in its condition where y2 when x is 0 is equals to 1 above. Plus 3 times y1, which is 2 minus x squared, which is the value of x is 0. So we have here x 0 squared times y2, which is 1, times its step size 1. So we have 1 plus 6 minus 0 times 1. So we have 1 plus 6. So y2 when x is 1 is equals to 7. So that would be all in this problem.
So here's another example for Euler's explicit method. Here we're gonna look at the second example of the Euler's explicit method for solving differential equations directly. Now these are the formula for Euler's method, and the last line is the line that we're going to use filling this information. So we're going to use Euler's method for approximate value of the solution of the initial problem y equals x squared and y 0 equals 1. So here's another example for Euler's explicit method. Here we're gonna look at the second example of a Euler's explicit method for solving differential equations numerically. And these are the formula for Euler's method, and the last line is the line that we're going to be using filling this information. So we're gonna use Euler's method to approximate y value y of 0.9 of the solution of the initial value problem y prime equals x squared and y of 0 equals 1. So initially, we're starting with the so you have to use Euler's method. So it says the first y value that we're going to approximate is so if not integration x value, this case, our x sub 0 is not gonna end up with those 4. So what the second one is, we just have 1 plus 0 plus 2 times 0 squared. That's just gonna give us plus 1. So our x value is 4 and the y value is 1.
So initially, we are starting at 0 and we are using step sizes of 0.3 to eventually approximate the y value associated with 0.9. So we'll have to use Euler's method a couple times. So we're gonna fill in this formula. So it says the first y value that we're going to approximate, and this is gonna go with 0.3. Well, that's going to equal the original y value plus step size h, and then we'll have to take f of x sub 0 times or fx of 0 and y sub 0. Okay, so our y naught value, that's the value that we're starting with. And it says that our initial y value is going to be y equals 1. And then we take our step size of 0.3, and then our capital F represents the derivative. So it says we have to plug in the value x sub 0 and y sub 0 respectively for x and y. So we'll plug in the initial x value. In this case, our x sub 0 was just 0. So we're gonna end up with 0 squared. So if we simplify this, we just have it 1 plus 0.3 times 0 squared. That's just gonna leave us with our initial y value of 1. Okay, so now it says our x value 0.3 and the y value of 1.
So our y sub 2, it says we will take the y1 value plus again our step size of 0.3, and then we'll have to take f of x sub 1 comma y sub 1. So again, this is going to be our x sub 1 value, and this is going to be our y sub 1 value. So it says y1 is 1 plus 0.3, and now for the derivative, we have to plug in 0.3 for x and 1 for y. But again, there's no 1 in the derivative formula, so we're gonna take x squared, which is 0.3, and now we'll have to simplify 1 plus 0.3 times 0.
So our y sub 2, it says we would take the y1 value plus again our step size of 0.3, and then we'll have to take f of x sub 1 comma y sub 1. So again, this is gonna be our x sub 1 value, and this is gonna be our y sub 1 value. So it says y1 is 1 plus 0.3, and now into our derivative we have to plug in 0.3 for x and 1 for y. But again, there's no y's in the derivative formula, so we're gonna take x squared, which is 0.3, and now we'll have to simplify 1 plus 0.3 times 0.3 squared. So we've got, I guess, 0.3 cube. I guess that shouldn't be too terrible. Plus 1.027. That's gonna be our approximation. So the approximate y value that would go with 0.6 would be the y value of 1.027. And now we have to simplify, do this one more time.
So our third approximation is going to be y sub 2, again, that's the step size of 0.3, f of x sub 2, y sub 2. So we're going to plug all those numbers in there. So again, y sub 2 is 1.027 times 0.3. Again, our derivative only involves x squared, so we're going to 0.6. And now if we can simplify this, and we're getting 1.135. So we've now done this a couple of times, so it says 0.1 approximate y value again. So we've now approximated. We can say y of 0.9 is going to be roughly equal to 1.125.
So our third approximation is going to be y sub 2 again plus the step size of 0.3 f of x sub 2, y sub 2. So I'm going to plug all those numbers in there. So again, y sub 2 is 1.027 times 0.3. Again, our derivative only involved x squared, so we'll plug in 0.6. And now we can simplify this and we're getting 1.135. So we've now done this a couple of times. So it says at the point 0.9, our approximate y value would be 1.135. So we've now approximated. We can say y of 0.9 is gonna be roughly equal to 1.135.